Okay, thank you all. My name is Martin Hilgeman from Dell, and I'm in the European HPC group, mainly involved with benchmarking and applications. So my talk will not be about Dell hardware, but I will rather talk about some investigations that we are doing. I have to emphasize that it are investigations, so it's not related to any Dell product offering for now or in the near future. So it is just, like I said, some work to find out whether we can save power on the MPI level. So firstly, I will go through a definition of system load, some observations that I see, some MPI basics for you who are not very familiar with MPI. Then some processor features that we do have, whether we can save power using that, and then we'll put it all together using a library and show you some benchmarking. So if we just look at an average HPC application and we use the top utility in Linux, and this is an MPI application, then we have all cores in my system. This is a Sandy Bridge node. We have all 16 cores doing 100% of the time something inside my application. So, well, looks good, you can say. All cores are busy, computationally intense, 100% busy, full power, etc. But actually, is it doing something useful? We don't know that. So, the application that I mentioned, in fact, it is LS-DYNA, so very well known in structural mechanics and at CFD. It's the in-core solver, and it is parallelized with MPI. So Intel MPI, platform MPI, Open MPI, even you can use all different kinds of MPI library underneath LS-DYNA. But actually, if you look at the stack trace of one of the processes running on core 11 here, then you see that it is in the wait state. So it is actually sitting in an MPI barrier. You can see that here. And it is waiting for an acknowledgement of the barrier, or it is waiting for something to arrive. So 100% busy according to top, but actually it is sitting in a spin wait loop. Another core shows the same symptom. It's not MPI barrier, but it's MPI wait, waiting for probably a direct I send, I receive completion here, being called from my wait function in LS-DYNA. So the bottom line here is waiting for data can also be very CPU intensive. Something about MPI. I think most of you are familiar with MPI, but it is important to understand what it does, because I will make use of the MPI basics in order to do something with it underneath. So just to repeat this, it's a very generic programming interface that allows you to run an application in parallel over a number of distributed machines. So the machines are not sharing memory, they are independent entities, and they are being connected with each other through, as we know now in HPC, through a fast network, which is commonly InfiniBand nowadays. And then the data is being transferred as messages. And those messages, you can see it as some kind of express service where you send an envelope, and on the envelope is the name of the target. And then inside the envelope, there is the information that you are going to send. And you also have a reference tag, because you have to keep track of what is actually being sent and received. A send and receive is also two-way. So you send something, but you also want to know whether it has been received or not. So in a standard MPI, and you do a send, then you have to wait for an acknowledgement for the receive. So here I have node 1, and my simulation is not working, and it broadcasts portions of an array to other nodes. They get it back, and they do their calculation, and then they send the result back to node 1. Very common communication pattern in MPI. So what's happening, actually, or what could happen in case of of the weight that I showed you, or the barrier. So let's assume that we have two cores here, two MPI ranks are sitting here. Here's one sitting and here's one sitting, and both ranks are doing their computation inside the function, inside the solver routine. Core 1 is done and sends something to core 2. But actually, core 2 is still busy with its computation. And we have a load imbalance here, you could say, because of the domain decomposition that is being done that is not balanced, or we have some kind of unstructured grid so that we don't have a uniform load distribution. It can all happen in all kinds of segments. So core 1 does its send, and then it sits and waits because MPI send is blocking, as we call it. So it blocks, keeps waiting for the matching receive that eventually comes back after core 2 is done with this computation, then posts the receive back to core 1, and then they continue. So it is this wait time that does the polling that is very CPU intensive. So can we do something here? And why has it been designed like this? Well, actually, HPC is about maximum performance. So if we do communication, then communication is overhead. And we want the overhead of communication as low as possible, because we are interested in the computations itself, because that gives us results, and the communication is just necessary because we want to run parallel. So all MPI libraries do polling, and what they actually do, and I think that's not here, it's on a later slide, they keep asking the network interface whether there's any incoming data for them, based on the message tag, based on the queue pair information underneath, if you have InfiniBand. So if you just poll aggressively, then you hopefully will also minimize the latency. The more aggressive you poll, hopefully you will get a faster answer, because you are not doing something else in the meantime. But the reality is here, because this all works fine, the polling, if you have a very well scaling application that is very balanced and very parallel. But, well, we know Endel's law, not all applications are embarrassingly parallel. So most chemistry applications, for example, well, you are happy if you achieve 98% parallelism. So there is always a serial fraction. And we know from Endel's law that if you scale up, and this graph shows you an application that is 80% parallel. So if I scale up from 1 core to 2 to 4 all the way to 32, then you can see that my parallel fraction decreases in terms of wall clock time. So, but actually, the serial fraction of 20% stays the same. So I'm using 32 times the number of cores, but actually I'm only getting a speed up of around 4.5. See, this is common knowledge, but important. And the second reality is, and this is again for LS-DYNA with the unstructured grid, but it's also true for other applications. If you have load imbalance, and this graph shows you the MPI rank here on the x-axis and the wall clock time here, then you can see the application time is, or the calculation time you can say, is here in purple or in red. And it's very unbalanced. Some cores are doing more than others. And then eventually everybody has to be at the same level. So if these cores are done with their computation, they eventually have to wait for the others to be at the same level as well. So very unbalanced. So then I thought, can we do something smart during these wait times, during the load imbalance that we have, whether it is due to an unstructured grid or the decomposition, or perhaps it is due to a serial phase that we have in the application. Can we do something smart? And at the same time, by doing something smart, can we also achieve something else? Can we, for example, make the processor use less power? Or can we perhaps also improve performance because we do something smart at these wait times? Then I looked at the hardware features that we have in the CPUs, and now most modern CPUs have what they call processor P states or power states. It's also known as dynamic voltage scaling, so you reduce the voltage on the CPU and then also the frequency drops of a CPU. The normal state is P0, where the processor operates at maximum power and its maximum performance, and then there are, according to the specifications, up to 15 states below, all with less power usage and less operating frequency. We also have turbo states on top of this, and both Intel and AMD do support P states. Intel calls it enhanced speed step, AMD calls it power now, and they are part of the ACPI advanced configuration and power interface specification. Actually, this was being tailored mainly for mobile devices, because that's all about saving power. It's all about also be able to suspend and resume systems, but server-grade processors that we use in HPC also support ACPI and the motherboards as well. Not only Dell, but every vendor does this. Sorry. And then also very important, the Linux kernel does have a uniform interface both for Intel and AMD CPUs to do something this on a per core level. So in case of a 16-core AMD file driver chip, I can actually control them all independently based on the power that I give, and then the frequency goes either up and down. The other side of the P state is turbo mode. AMD and Intel also have turbo mode. They're all they do it slightly different, but the idea is the same. If all 4 cores are busy here in this graph, then they all operate at their nominal frequency. The Intel Sandy Bridge chip and upcoming Ivory chips support also a feature that they can, based on the environmentals, they can operate above their nominal frequency for a very short period of time. And if some cores in the same socket are idle, then the other can hit turbo mode, and then they can operate at an even higher frequency. And here, if there are even more cores idle, this is true both for Intel and AMD, then even the cores or the frequency of the still active core can even be higher. So, if I look at my goals again, where I said, can I make the CPUs use less power, and can I also improve performance at the same time? Sounds like a very ambitious goal. So for the first one, I can then put the processor into lower power state. And for the others, to improve performance, well, perhaps if I have that load imbalance that I showed you, perhaps they can use their turbo mode. I have a slide here that actually shows you this. So this is what I showed you before, where we have 2 cores, 2 MPI ranks doing its computation. This one is done, does an MPI send, the other one is still busy, and this one is waiting. So let's then assume that we do this with power states. Then here they are at a nominal frequency. This is Sandy Bridge E5 2670 operating at 2.6 gigahertz. This one is done, does the send, and after the send, it is waiting, it goes into its lowest power state, which is at 1.2 gigahertz, the processor time. The other one is still busy, and actually sees that some cores at the same socket are at a lower power state, then this one could enter its turbo mode. So at the same time this one goes down, the other one could go up and perhaps even operate at 3.3 gigahertz instead of 2.6. And then, hopefully, at the end, we have a speed up because we can do the remainder of this first computation faster because we do it at higher frequency than before. So how do we implement this? part of the MPI standard that we have, and there will also be a talk about MPI 3, and this is still also in MPI 3, is that you have a profiling interface. So while your application does do an MPI call, so either an MPI send or MPI barrier or any other MPI call, internally a function called P of Peter, PMPI, is called. So what you can do actually is do something smart with it. So I firstly, in order to do this, I identify the MPI functions that can make use of these power states, and the most obvious targets here are the blocking functions. So the blocking functions that wait for an acknowledgement. So blocking functions, point-to-point functions here, are send, receive. We have barrier, which is collective, and also blocking, and we have wait, which is also blocking, and we have the exchanges as well as being point-to-point here. You could do the same for collective MPI functions, so all reduce, all gather, all to all, every MPI function that has an all in it. It's very communication intensive. These functions also have an implicit barrier in them, so everybody has to arrive at the same level eventually and has to call this. So it can also be a good target for something like this. Then what I did was the following. I wrote my own MPI receive wrapper here, and like I just told you, internally inside the MPI library, PMPI receive is being called. So I enter the function, I set the CPU frequency to its lowest power state here. Then I do the actual receive, and after the receive is done and I get a good return value from the call itself, I then put CPU frequency up to its original level. This is a very simplistic picture because there is a lot of tuning that you can do underneath, because if my receive is, for example, on the same host, then the receive is being done not over the wire, but it's being done using shared memory. So then this can give a lot of overhead. We also don't know whether the application is imbalanced or not, so we also have to keep track of this somewhat. And lastly, if I have a very small message size, so the count of the buffer is very low, so I'm only sending, for example, 8 bytes to my neighbor, then it does not make much sense to do all these kinds of things for only 8 bytes that I'm going to send. So how did I do this? I wrote a library that I just call here del toolbox.so, and the library has all the MPI functions in it with the original name. The application has symbols, unresolved symbols that have to be resolved by an MPI library, and I preload my library so that the application function calls picks up my MPI functions instead of the functions of the MPI library. This is very transparent. I don't have to relink or recompile my application. I just preload my library, so I can use it for all applications using MPI, C or Fortran. I will both have C and Fortran bindings. And the only thing that I need to do is I have to make sure that I have a version available for the MPI library that I'm using. So it works with all MPI libraries. I tested Intel MPI, OpenMPI, MPI-CH, and its variants, and I also tested Platform MPI, and it just works. The only thing is, if I'm going to downclock CPU cores, is that my library needs to have knowledge about which CPU core it has to lock down. So I don't want my application to migrate across cores during its execution. So I have to use some kind of pinning or affinity tool. So this is my own affinity program, Del Affinity. I talked about this last year at this conference in Malaga, but it is just some kind of more advanced numeric control. So there are various tools available. It allows you to pin processes to processor cores. Then my library, after it knows its core, it also has to know the process IDs. The kernel works based on process IDs and not based on MPI ranks. So there has to be some kind of translation as well underneath. Then I have to find out whether what I'm doing makes sense, because I'm introducing overhead, because I am fiddling with hardware that I'm going to put into a lower frequency state, and it has to be worthwhile to do so. I looked at MPI libraries and how they do their polling for incoming messages. The documentation is very sparse, so I know from OpenMPI that it polls every 10 milliseconds and then yields the CPU. Intel MPI does do some kind of spins. Platform MPI and FFH spin as well, and then they yield the CPU. And what I mean with yield is that it then calls a system call called scat yield, and it says to the kernel, I'm done, I have nothing to do, so if you have something else available that you could schedule on this core, please go ahead. But actually, in all HPC applications, there is nothing to be yielded, because I am the only user of a node. So this does not make much sense, and in practice, it just keeps executing the spin wait loop. Then I had to measure whether the frequencies p-state switching that I'm doing makes sense. Like I said, it involves latency. So if I go from, it's a typo, I'm sorry. If I go from 2.7, which is some kind of turbo mode, to 2.6, then the minimum latency is around 4.5 microseconds, even to the lowest processor power state. So we are used with InfiniBand that we think in terms of microseconds. If we talk about a 8-byte or 0-byte message, then we say 1 microsecond. You can say here that it's 4 microseconds, so it's 4 times slower, so we have to be careful if we do this. Then there's another nasty side effect, is that I find out that the switching inside the kernel is not performing uniformly. So I also had values like 25 microseconds. I found also undertakings inside the kernel community that they are trying to fix this generally, so that fiddling with the sysfs interface, what I'm doing here, is being done more at a real-time level or more at a predictive uniform performance level, but this is something that is not very nice. I said just an investigation, remember? Then we also have to make sure that the polling time, so I showed you the polls, and I have to make sure that it does not sacrifice performance if I run at its lowest frequency. I don't want the performance of my MPI library to be degraded because I am running at a lower frequency. I looked at the polling time and I found out that it is degrading somewhat, but not that much, and I still achieve 10 milliseconds here for the lowest power state. So I could say that's fine, that is within the specification of OpenMPI, for example. If I run at 1.2 gigahertz, then I am not wasting any additional performance. And then, does it also save power, the processor p-states? Yes, it does. I ran HPL on a node. I started with around 240 gigaflops here, and with this is the power. Yeah, it is 310 gigaflops for E5 2670, and I use around 200 something watt. This is being measured on both CPU sockets. So this is not system power consumption, but it is power consumption on the CPU socket level. I have 2 sockets. This is a 115 watt CPU, so yeah, it's somewhat around 230 watts. Fully utilized. And when I go to lower frequencies or lower P states, then I get a power of around 80 watts in its lowest P state, 2 CPUs. So indeed, 63% less power compared to its highest power state. And actually, you can also see that the processor becomes more efficient because my performance level is degrading less than my power consumption. Interesting side effect. So, what does my library show you? Well, at startup, it says first that the process ID, because it's MPI based on process IDs, externally is pinned to whatever CPU core number, and that for these CPU cores, it finds out that the current frequency is 2.6 gigahertz, its lowest frequency is 1.2 gigahertz, and its maximum is 2.601, and this means a turbo mode. So it's not the actual frequency, it is the Linux kernel saying we can do turbo mode on this processor. And then I do this for all MPI ranks or processes. Where are they pinned on which host and what are the... At the end of the run, it shows you then the total MPI wait time. You can also see that the wait time, because I'm showing the same two CPU cores on different hosts, is not uniform. And it shows you the number of frequency state changes that it has done. The flip-flop of going from a higher to a lower P state. And you can then also see the amount of time that has been spent in frequency scaling itself. So this is the overhead that I'm introducing because of the switching in frequency. I also ran some the whole suite of NAS parallel benchmarks, the Type D, so the almost largest ones. I did run this on 64 cores, 4 nodes, and you can see here. I also ran some on the more cores. This is the power consumption here for both CPU sockets, and this is the as is. And with P state, I mean the performance that I get by actually doing something with the frequencies. You can see that the walk time is slightly more for most kernels, around 3 or 4%. Some are actually faster, so the turbo mode is working for some kernels. And you can see the delta in power consumptions, So for some loads, like the BT kernel, it is not making any sense at all. But for some, it can. 12%, 20%, 10%, 4%. I mean, if you think big and you think about exascale levels of performance, then this could be interesting. So what's the status? I said it is just an investigation. The library works with all major MPI libraries at this moment. I tested it on a small range of applications, but in different segments. So I tested WRF, the weather forecasting model, CP2K, so the ab initio plane wave material science code, FASP, because I'm very familiar with FASP, another plane wave code doing all-to-all communication. I mentioned LSDyna, and I also tested Chromax. So I could say performance looks okay-ish, but there's still a lot to be done and a lot to be tuned. So what's on my to-do list? Well, a lot, if I want to do something. The frequency scaling does require root privilege, so I either have to write another wrapper library running as root, or have to do something fancy during the boot process that I'm allowed to do this. And I found out that the P-state switching is not uniform in performance. So it is around 5 microseconds, but I've also seen 15 or even higher. Where can I use it? Well, a lot of tuning to be done, and I also have to do more on the benchmarking, more on the power measurements on the whole system level, because at this moment I'm only measuring on the CPU level. Okay, I have more, but that's something else, but I'm now just on time, so I will leave it for now. Any questions?